But thank you everybody for coming. My name is Michael Hall. I'm a developer evangelist at ARM. And today I'm going to be talking about running Java applications, server and cloud applications specifically, on the latest ARM hardware. So first, a little bit of background history about ARM. Our history starts in 1978 with a little company called Acorn Computers based out of the UK. This was at the start of the whole PC, personal computer revolution. They were contracted by the BBC, the British Broadcasting Company, to develop the BBC Micro. This was part of a program that the BBC had going on to try and educate the general public on the use of personal computers so that they can understand what they are and how to use them. So that was all back in 1981. The BBC Micro used a MOS 6502 processor, as a little 8-bit processor. And Acorn quickly learned that it was not quite up to the task of what the BBC wanted to be able to do. So in 1985, they developed their own microarchitecture and CPU that was called the ARM1. So before there was a company called ARM, there was a CPU called ARM. And in 1987, they used that in their first branded PC, the Acorn Archimedes. Then in 1990, Acorn Computers partnered up with Apple and what is now NXP Semiconductors to form the Advanced RISC Machines Limited, or ARM, which was the start of the company known as ARM. They developed processors that made their way into the Apple Newton, which was the very first handheld personal computer that was launched by Apple in 1993. And then in 1998, it was included in the Nokia 6110, which was the first GSM cell phone to have an ARM CPU. And ever since then, we have been in just about every cell phone that has been on the market, especially every smartphone, every flagship smartphone from the get-go has had ARM processors in them. A lot of other stuff happened in the mobile space and other spaces, so I'm going to skip ahead to the milestone that's going to be important for this talk, which was the introduction of our 64-bit instruction set architecture in 2011. This was an expansion of the ARM32 architecture that had previously been in use. Who knows what this is? Yeah, don't read the attribution link that I'll give you. Yes, it's a Raspberry Pi. Most people at this conference that I've talked to, when I've talked to them about running Java software on ARM, this is what they think of. They think I'm talking about running it on a Raspberry Pi. It is a very popular little board. It's got 2 or 4, depending on the generation, ARM cores in it. It's a great little development platform, but that's not what I'm here to talk about today, because ARM is a lot more than just this. On the small end, we're in microcontrollers. This is a Raspberry Pi Pico. This uses a custom CPU that Raspberry Pi Foundation developed called the RP2040, and it is tiny. I've got one right here. It uses a reduced size instruction set from the regular ARM processors so that your embedded programs can be even smaller. That is on the very small end of the spectrum of where ARM sits. On the far other side of that spectrum, however, this is the Fujitsu, I'm going to try and pronounce this, Fugaku supercomputer. This has 158,000 CPUs that Fujitsu designed. Each one of those CPUs has 40 high-performance ARM cores in it. So all told, this was a little under like 8 million CPU cores running in this supercomputer. And when this launched in 2020, and for a little while after that, it was the most powerful computer in the world running high-performance ARM chips. So we now go from the very, very small microcontrollers all the way up to the highest of high-performance computing. A little bit of nomenclature, because we have a lot of brand names that can be confusing sometimes. Most ARM CPUs fall into the Cortex line, and they all have a letter after them. And to make it easy, the acronyms spell out ARM. So if you see Cortex-A, think about multiple application use cases. So desktops, laptops, servers, even supercomputers, but where you're running multiple processes in a larger environment. The R you're going to see less of. They're not quite as common, but that stands for real time. You will see those primarily in like automotive use cases where you do need more power than a microcontroller, but you still need it to be real time for safety issues. And then the Cortex-M is what you'll find in the Raspberry Pi Pico and the Arduinos and a lot of custom microcontrollers. These are tiny, tiny little low power, low footprint microcontrollers. You might also see Cortex-X mentioned sometimes. The Cortex-X are customizable cores that are specifically used for companies who want to have specific control over cache sizes or memory bandwidth. You'll see these in some of the flagship cell phones, like the newest Pixels pair high-performance Cortex-X core with a super low-power Cortex-A core so that it can scale down to save battery life when you're not doing something super intensive. These are also used in laptops. So the Lenovo X13S has got I think it's a Qualcomm chip in it that uses some of these custom cores as well. More recently, we've launched the Neoverse brand, and these are specifically designed for high-performance use cases. So cloud computing, HPC, even more powerful edge devices. And that's going to be the focus of the talk today. So let's talk a little bit about those high-performance ARM CPUs. Back in 2018, Amazon launched Graviton1, which was kind of a game changer for the server computing, the cloud computing environment. This was the first custom chip by a cloud manufacturer. It does use, these use the Cortex A72 cores. They actually launched this before Neoverse was its own brand. So the Graviton1 had 16 of these cores in it, and it used the ARM V8A instruction set, which was the first to introduce the 64-bit instruction set, so AArch64. Then they came out in 2019 with Graviton2 that had 64 Neoverse N2 cores, so the first ones using Neoverse architectures, and they got a nice version bump in the ISA that they support there. This added some vector extensions that improved performance for a lot of mathematically intensive operations. In 2021, they added Graviton3, which again has 64 cores, but these are using Neoverse V1. And just like the Cortex line, there are different types of Neoverse cores. The N1s are designed to have a balance of performance, power usage, and die size. The V1 cores are designed to lean more heavily into the performance. So they'll use a little bit more power, they'll be a little bit bigger, but you get a lot more bang for your buck out of those V1 cores. And those are starting to become the more popular ones. Then in 2023, last year, they announced Graviton4. These are going to have 96 cores of those Neoverse V2. And this boosts it up to the ARM V9 instruction set, which adds even more vector extensions for things like multimedia processing, signal processing, or specifically nowadays for AI, for training, and also for predictions. But Graviton's really only available on AWS. If you want to run Graviton anywhere else, you're out of luck. That's the only place you can get it. You can't actually buy a Graviton chip. You can just rent space on one of those. If you want to buy chips or you want to run something on your own data center, your own offices, there's a company called Ampere, and my friend Aaron is here representing Ampere. They make ARM64 chips for servers. Back in 2020, they launched their Ampere Ultra, which had 80 cores, and I don't know which version of Neoverse those were. I couldn't find that on your website. It's Neoverse something. What? 8 plus? Oh, that's version number. That's not. That's okay. Okay. Then in 2021, they followed that one up with the Ampere Ultra Max, which had 128 cores. I should say up to 128 cores because you can get these in different sizes. I think the smallest one is 32 cores though. Also in 2021, Ampere chips started to be used in Oracle Cloud. It also started to be used in Tencent and ByteDance over in China. Scaleway, Equinix in their data centers where you can get bare metal access to these chips, and Cloudflare as well. And then in 2022, they were adopted by Google Cloud and Microsoft Azure, and also Hetzner over in Europe. So 3 of the 4 big cloud providers here in the US, Oracle, Google, and Microsoft, all running Ampere chips. And then last year, they announced the Ampere 1, which has a whopping 192 cores in it. So a real monster of a chip. And this has got an asterisk next to it because it's not technically a Neoverse core. They're a custom core design that they've developed outside of that range, but still designed for these same kind of use cases. So I wanted to include it here. A lot of people don't know that NVIDIA makes CPUs. The Grace part of their Grace Hopper combination is a 72-core Neoverse V2 CPU. So they pair those with their GPU, and that's powering a lot of their AI infrastructure right now. In addition to that, they also have what they call the Grace Super Chip, which instead of pairing a CPU and a GPU, just has 2 of those high-performance CPUs in it. So you get 144 cores there. If you are doing something that can't be optimized by running it on a GPU, you can run it on one of these and get twice the performance. And then last month, they announced Grace Blackwell, which is their latest GPU cores, but they're still pairing that with these Grace ARM-based CPU cores. So even the next generation of NVIDIA's AI infrastructure is going to be running on ARM CPUs. Microsoft last year also announced that they're manufacturing ARM-based CPUs for Microsoft Azure. So they announced the Cobalt 100, which has 128 Neoverse N2 cores, and again is that balance between performance, power usage, and size. These are currently used internally by Microsoft engineers. They are not something that you can use on Azure just yet yourself. So if you launch an ARM instance on Azure, you're still going to be using those Ampere cores that they've already had out there. And then just 2 days ago, requiring me to update my slides, Google announced that they're going to start, well, actually, they announced they already have been manufacturing their own ARM-based CPUs called Axion. They are Neoverse V2 cores, and I've got very limited information about them right now, mostly just what they put out in their press release, so I don't know how many cores that has, but they did say it's already running certain Google services, so things like Bigtable, BigQuery, Google Earth, and YouTube ads are already running on these custom ARM cores. And supposedly this will go GA later this year. They didn't say exactly when. I don't have a picture of theirs, so you get a QR code to their press release, so you can find out more information about it there. They make some pretty big claims in that press release. Again, this is coming from Google, but they say it's 60% less power usage than their current generation x86 chips and 50% greater performance out of them. So big claims, like I said, it's all right there coming directly from Google. So that's the hardware support. It's already out there. It's in all of the clouds and most of the data centers that you might want to run in. So let's talk about the ecosystem. Back in 2013, unsurprisingly, Debian was one of the first Linux distros to gain AArch64 support. And because of that, so did Ubuntu. This was followed up in 2015 by SUSE and OpenSUSE and also their enterprise offerings. And then Red Hat joined the party in 2017. Then in 2018, with the launch of Graviton 1, Amazon also released Amazon Linux for AArch64 so that you could run their favorite Linux distro on their favorite cloud CPU. And then thanks to work between Microsoft, ARM, and the Linaro project, we now have Windows on ARM as an option. So Windows 11, full version of Windows 11, not the RT ones that we had in Windows 8 time period where it was like a stripped down version of Windows. This is the full thing running natively on ARM CPUs. You can get this on things like that Lenovo X13S I mentioned earlier. As far as your containers go, Docker has full support for ARM64, both for building and for running. So you can use Docker BuildX and target ARM64, either make a dedicated container to that or make a multi-arch container. Podman also has full support for running these containers. So if that's your preference for running them, you can do that. And Builda, which Podman uses under the hood to build those containers, is capable of building, again, a standalone ARM64 or multi-arch containers. Cryo, which is the runtime that underlies a lot of other frameworks, has support for that. So if you're running a framework that uses Cryo under the hood, you're covered there. Linux containers also has native support for it, and Incus, which is the open source fork of LXD. So for, again, building and managing Linux containers on ARM64. And then Containerd, another popular runtime environment for Docker and OCI containers, has support for that. Even Apache Mesos, if you're running something like Hadoop on Mesos and you want to move those workloads over onto Graviton or one of those Ampere systems, you can do that now too. And if you're using build packs, there are Java build packs for ARM64. These are provided by Paquito, and they use the Liberica JDK as the default for that, although I think you can change which JDK you use because there are other options, but that is the default. For CI/CD, GitHub is a popular option. If you're using GitHub Actions, you've been able to use self-hosted runners to run on ARM64. They also have been working on hosted runners, so you will soon be able to use those and not have to host them yourself. They didn't give me any kind of time frame for when that was going to be. I was told coming soon back in November, so your guess is as good as mine when they're going to actually release that. Similar story with GitHub. You can use self-hosted runners with GitHub's actions or GitLab's actions. There is a discussion thread. They do everything public, which is nice because you can kind of see a lot of the internal discussions happening. So there is a discussion happening on having hosted runners for ARM64. That's still very much in the thinking phase. So they don't have any solid time frame for that yet, but they are talking about it and know that there's a demand for it. And then CircleCI has got support for it, both in their cloud offering where they run everything for you, as well as their server offering, which is where you run CircleCI on your own cloud instances. So if you're running on AWS or something, you can run that on your instances, but still managed by them. That currently only supports Amazon right now. They're looking into expanding that to CircleCI Cloud on GCP and Azure. And just like GitLab and GitHub, you can run your own self-hosted runners for that. Even Travis has support for it, so if you're still using Travis, they've got two options. They've got a generic ARM v8 option that will run on just about any ARM server CPU. They also have one specifically for Graviton 2, which is, I think, only available through their commercial offering, if I read their documentation right. But it does have optimization specifically for those chips. And then Jenkins, both the controller and the agent, you can run on ARM64 as well. So that's an option still too. For deployment, everybody's favorite Kubernetes has native support for ARM64 there, as well as all of the big four cloud providers' Kubernetes offerings. So Amazon EKS, Google GKE, Oracle OKE, and Azure AKS. We're so creative with names. All of them have support for running on their respective ARM-based nodes. And the nice thing about this is you don't have to go all in. You can mix and match x86 and ARM instances in your Kubernetes cluster. So you can start deploying a mix of those. And depending on what your container type is, if it's multi-arch or ARM64, it'll pick the right nodes where it can run those instances. OpenShift, I know we've got some OpenShift users in here. They've done the work to make OpenShift run on ARM64 servers, so that's ready for you now to start using. And Rancher also by SUSE has got some initial support for that. Their managed Kubernetes, RKE, has full support for it. And then Rancher Manager, which is their orchestrator, has got experimental support so far. I just checked with them yesterday to see if that was still the case. And Manager is still experimental. RKE is available in production for ARM. And there's a lot more software and frameworks than I could list on these slides. So we've built a dashboard where you can find all of that information. You can scan that QR code to go to the dashboard and look up your favorite dependencies to see if they have ARM support and when they got ARM support. And the nice thing about this is that it's backed by our public GitHub repo and open for anybody to contribute. So if you want to get your software listed in there or a third-party software that you know has ARM support, you just click on that link, contribute on GitHub link at the top of the page, and you make a simple pull request. It's all based on Markdown, so it's real easy to make a contribution that way. and we're taking that from anybody. So help us build out this dashboard so people can find your software and make sure that it runs correctly on the latest ARM systems. All right, so we've gone over the hardware support, we've gone over the operating system and tooling support. So let's talk about support for Java on ARM. There's been quite a bit of work that's gone into the OpenJDK for this. The first one was JEP 237, which added the Linux ARM64 port. This was an interesting story because they actually started on this port before there was any ARch64 hardware available to them. So they ended up using ARM's documentation of the architecture to build a simulator. And then they started the OpenJDK port running on that simulator. But the documentation was so good that when they did finally get hardware, they said that there was very little that they had to change from what was running on the simulator to make it run on the real thing. In JEP 297, Oracle contributed their proprietary ARM32 and ARM64 ports that had been in their closed source JDK. That got contributed to OpenJDK as well. The initial port that Linux, the JEP 237 is still the ARM64 port that you'll get, but ARM32 support is now from that Oracle contribution. Then in JEP 315, there was a lot of work that went into Hotspot to add ARM intrinsics to that. So if you were in the talk just before lunch, I think it was, where he was talking about all of the ways that the JIT compiler is optimizing code, including using hardware intrinsics. There was a lot of work that went into using Intel and AMD's set of intrinsics previously. This JEP started adding the same things for ARM. So this is both vector extensions that I'd mentioned before, which are good for the big, bulky math calculations, as well as more simple instructions that can just be a little bit faster than running in Java itself, in software. So a lot of work went into that. Then in JEP 388, Microsoft contributed a port for Windows, so you can run on Windows on ARch64. And then JEP 391 came the Mac port, which was based partially on the work on the Windows port. So now you've got support for Linux, for Mac, and for Windows on ARch64 from OpenJDK itself. GraalVM also added support back in, well, I shouldn't say back. GraalVM 21 is where its support landed. That has been backported to now support OpenJDK's 11 and 17 as well. And according to their website, you can run the JVM languages, Java, Scala, Clojure, and Kotlin with GraalVM on ARch64, as well as Node.js and WebAssembly, but not currently Python or Ruby. But anybody running Java on GraalVM, building native images, you can do that now on ARch64. Amazon has their own build of OpenJDK called Corretto. That has support for OpenJDK 8, 11, 17, and 21 on ARch64. They have specifically optimized this for Graviton. So I don't know if there's code-specific optimizations in theirs that they haven't sent back to OpenJDK, but there's certainly compile time optimizations since they know exactly what version of the ARM instruction set Graviton supports. And this is nice because this makes it run better for things like running functions in AWS Lambda with Java. Liberica is Bellsoft's JDK. I didn't see a Bellsoft booth out there. I was kind of surprised by that. But I mentioned earlier they're the default for the Paquito build packs. They've done a lot of work optimizing OpenJDK for ARM64. And their JDKs support OpenJDK 8, 11, 17, and 21. And Azul also has a JDK for ARM64. They do have a booth right out here outside the door. Theirs also supports OpenJDK 8, 11, 17, 21, and 22. They also have their Falcon Jet compiler, or their Falcon Jet server, which is it's like IBM's JIT server. It'll run separate from your JVM and let you share resources. And they've done some additional optimizations in there that are really, really fascinating. There was a talk about it last year. I don't know if he gave the same talk again this year. But I remember his talk last year talking about some of the like speculative optimizations that they can do in Falcon. So that's really cool stuff as well. They're highly involved. And then I mentioned OpenJ9. I didn't even know about this one until I saw their talk earlier this week. So this is another new slide on my deck. But OpenJ9 supports OpenJDK 8, 11, 17, and 21. Their JIT server, which is their standalone JIT instance that is shared by multiple JVMs, has AArch64 support, and their Semiru runtime, which combines their JVM and the OpenJDK classes, also has full AArch64 support now. All right, so I've talked a lot about optimizations. I'm just going to kind of mention some of the ones that are available in the latest ARM cores. So Neon was the first that we introduced. This has advanced SIMD instructions, or single instruction multiple data. These are instructions in a CPU where you want to perform the same operation on a whole series of numbers. Instead of doing one instruction for each of those numbers, you can batch that up. So you can say, for these 16 integers, I want to run the same instruction, and it'll run all of that on all 16 of those integers in a single CPU cycle instead of in 16 CPU cycles. So Neon introduced that for ARM chips. It was mostly good for multimedia and signal processing acceleration. That's what it was designed for. And it allowed for either 64-bit or 128-bit vectors. So you can batch your calculations in those sizes. This was followed up by SVE, or Scalable Vector Extensions. And the real innovative thing here is, instead of having static 64-bit or 128-bit vectors, it's up to the CPU manufacturer how many or how big of a vector length they want to support. So the spec allows for up to 2048-bit vectors. That the Fujitsu supercomputer, I think, supported 1024-bit vectors. The different CPU manufacturers, Graviton and Ampere and all the others, will have varying lengths. But from a programming perspective, it doesn't matter. You'll use whatever vector length is there on the CPU. So the more they offer, the faster it'll run. It also introduced something called per lane predication. We already had predication on our instructions, where you can say, run this instruction if the value is 1 or 0 or whatever. With the introduction of these vector extensions, you can now do that on a per lane. So you can say, if I've got these 16 integers, here's a mask of which of those integers to run this particular instruction on, so that you can pick and choose what you want to do and not have to swap your vectors around all the time. It also introduced some gather load and gather store operations. These let you fill that vector with data coming from different parts of your memory space. So in one instruction, you can pull all of that data to fill your vector into that, do your calculations on it on the next CPU cycle, and then the third one, you push that all back to its original memory address locations. So again, taking these multi-step operations and combining them into a single CPU instruction to run in a single cycle. In the ARM v9, we introduced SVE2, which is a combination of those Neon instructions, the SVE instructions, plus a few additional ones to cover some more use cases. This is trying to be backwards compatible, so if you have something that's been compiled for Neon or for the original SVE and you're running it on a newer chip that supports SVE2, those instructions will still run. This also gives an overall performance boost to those kinds of vector operations. There's another one coming out called Scalable Matrix Extensions, which adds even more stuff for AI-specific workloads. I don't know how many people are aware of it, but there's ongoing work on a vector API in Java itself. It's currently on JEP 460 for JDK 22, but you can see there's a whole history of previous ones as they've been iterating over this API to get it into the main part of OpenJDK. And the goal of this is to provide a Java API that Java programmers can access that will reliably compile down to using these vector instructions on whatever CPU you're running it on. So what happens right now is you've got something like Hotspot, which will look at your Java code and it will see, okay, this is a pattern I recognize as vector calculations, and if it's running on a CPU that has vector instructions, it will translate it into those vector instructions And if not, it'll run some regular, slower operations. But that's all based on pattern matching and Hotspot being smart enough to know that it can do that with your Java code. The goal of the Vector API is to be explicit about that, to say, if you use this API, it knows exactly how to translate that into vector instructions that are optimal for your hardware. And right now that supports the vector extensions provided by Intel, which is, I think, AVX is their set of vector extensions, as well as Neon and SVE for ARM chips. So those are the two targets right now for the Vector API. The goal is to make it extensible for other CPUs in the future as well, but they're going to make sure that it at least works for those two different architectures so that it can be extended more in the future. That all happens in the C2 compiler. It's not replacing auto-vectorization in Hotspot. That's still going to be there. So when Hotspot sees something that it can optimize, it'll still try to do that. But in the future, once this API lands, hopefully everything that can make use of that will start making use of that so that you get predictable optimization out of that. And again, that's going to support Neon and SVE right from the get-go because we're working closely with the people developing it. I want to highlight some of the people who are doing this work, some of the companies specifically. Red Hat was the company who contributed that first Linux ARch64 port. If you're interested in the story on that, with them having to write a simulator and all, this is a link to that blog post. It was a really fascinating read. Andrew Haley and his team did that work. Everyone get it? Okay. Oracle, like I said, they submitted 2 ports, one of those which is a duplicate of what was already in there, but the ARM32 port was brought in, plus a lot of other stuff that Oracle has been doing around supporting ARM64. A lot more now. ARM's a first-class architecture for Java these days, so they've taken over a lot more of that work. Azul, they were the ones who did the Mac port for ARch64, so we can all thank them for Java running on our new laptops that have ARM chips that I can't mention the manufacturer of. And then Bellsoft, they did most of the work on those initial intrinsics in Hotspot, so that JEP 315 that I mentioned. They've also submitted a lot of optimizations to use of intrinsics and the JIT outside of the vector extensions themselves, backported those to LTS versions, and have also done some code cache optimization work, again on ARM64. And then ARM. We've been busy too with this. Like I said, we're working closely with the developers who are working on that Java Vector API so that we make sure that it's using the best ARM instructions on the latest ARM architectures. ARM also ported the Z garbage collector to ARch64, as well as the Java foreign functions API. And then we added JIT support for SVE extensions up to that maximum 2048 bits. Some improvements to Hotspot's auto-vectorization, various other code generation optimizations, and then just bug fixes and making sure that there's regression tests for ARch64 and that those are all passing. Now, since ARch64 is first-class architecture and OpenJDK, our engineers are focused more on enabling specific new features in the ARM architecture inside of Java, things like memory tagging for like memory safety and stuff like that. So more of that work has shifted out towards Oracle and the OpenJDK community and lets us focus on more kind of niche things. All right, so the hardware's there, the software ecosystem there, even the JVMs are there waiting for you. So how's the best way for you as a Java application developer to get started using these? One of the easiest ways is just to start using one of the cloud instances. Oracle has these Ampere A1 compute instances, either bare metal, where you can get 160 cores and a terabyte of memory, or they're flexible VMs, where you can get up to 80 cores and half a terabyte of memory. They also have this really nice, really generous free tier offering. That's why they're first on my slides because I like their offering the best. That'll get you 4 Ampere Ultra cores and 24 gigabytes of memory that you can partition however you want. You can put this all into a single VM with 4 cores and all the memory, or you can split it up into 4 different VMs, or however you'd like. And the nice thing about the ARM cores is you're not getting virtual CPUs. You're not getting a thread in a hyper-threaded CPU core. You get the entire core to yourself, so you don't have to worry about noisy neighbor problems there. So you get 4 dedicated cores that are always there for you in this program. And they're always free account. There's no risk of you running over the free usage and getting a surprise bill at the end of the month. They ensure that that's not something that's going to happen. They also have, they call it the ARM Accelerator Program. If you're doing some work that exceeds these free tier resource limits and you want a little bit extra to help you get started, they do have this ARM Accelerator Program where they can get you some additional free resources. You just have to reach out to them and talk to them about what you're doing. Amazon, you've got a few different options on which instance types you want. The M7G has got their Graviton 3 cores. That's, I think, the most up-to-date Graviton cores that are currently available. I don't think Graviton 4 is available yet to start using. You can get up to 64 cores there and up to 256 gigs of memory. They also have the M6G, which has 64 cores, but they're the Graviton 2 instead of Graviton 3. And again, up to 256 gigs of memory there. And then their T4G, which are their smaller instances, where you can get up to 8 cores and up to 32 gigabytes of memory. And these are available for Amazon's free tier, so you get up to 250 hours free of the T4G.small instances. That'll get you right at a month of full-time use out of one of these VMs. So a way to get started on Amazon without paying for it, at least for the smaller instances. And then Google Cloud has got the Tau T2A. Again, these are the Ampere chips. They're new ones. The Axion chips are not available for the rest of us to use yet. But you can use this instance type to get the Ampere chips up to 48 cores and 4 gigabytes of memory. They had been running a free trial to get people using these instance types. It just ended at the end of March. So I'm on their case to try and get them to renew that program and make that available. So keep an eye out. Hopefully they will do that again. And then Microsoft Azure has got a few different instances you can choose from. They've got both the high memory DPS v5, which has got up to 64 cores and up to 208 gigs of memory. The DPL SV5, which has got the same number of cores, but up to only 128 gigs of memory. And then there's smaller instance, that EPS v5 with 32 cores and 208 gigs of memory. So if you have an application that's more memory intensive than CPU intensive, that's a good option for you. And just like Google Cloud, Cobalt CPUs are not available to the rest of us to use on Azure just yet. So these instances are all still running the Ampere chips. And then Equinix, if you want bare metal to run your software on, they've got a bunch of data centers that are running these chips. You can get up to 80 cores of the Ampere Ultra and up to 256 gigs of memory. If you're part of a CNCF project, they're offering free resources to any CNCF project who wants to run parts of their CI/CD pipeline on Equinix machines. So that's a really nice offering there. For everybody else, they do have a $250 credit program, so you can reach out to them and ask how you can get access to that to get yourself started. ARM also offers what we call virtual hardware. These are, we've got this thing called a fixed virtual platform, which is a software simulation of specific hardware. Instead of a generic ARM VM like you would get from QEMU or VirtualBox, these emulate specific hardware. We used them initially to give people a development platform before hardware is available to start working on software. We've partnered with a company called Corellium to run these as a cloud service. So you can go to avh.arm.com. It is currently in a public beta, so you do have to sign up to request access to that. But that'll let you access various different hardware types. Again, all simulated. There's not real Raspberry Pis running up there on the server. But as far as your software knows, it looks exactly like a Raspberry Pi. You've got access to all the specific hardware, the GPIO pins. If you're running something like the IMX8 board, which has built-in sensors, there's an interface where you can say what readings you want those sensors to give the software running on that. More focused on embedded programming than cloud computing, but if you want to run a generic Linux VM or just try out a Raspberry Pi or something, you can do that too. That is free up to a certain resource limit, and like I said, it is currently a public, or it is in public beta right now. You do have to request access. We also launched a website earlier this year called Works on ARM, where we're trying to pull all of this information together in one place where you can find out where you can run your software on ARM servers and what different offerings and programs are available for use. So the ones I mentioned, like Amazon, Google Cloud, Azure, those are all listed on there. More than just those three, that's just where the screenshot cut off. So a lot of good resources there for you. And I'd also encourage everybody who's interested to join our ARM developer community. This is a community, worldwide community of software developers who are wanting to run their software on ARM CPUs. Traditionally, ARM has only targeted hardware and like firmware developers. This is kind of new for us to start looking at the top of the software stack. But that's where the interest is right now. People are seeing Graviton or these instances on Google Cloud where they can save money by switching off of x86, and we need to be talking directly to them about how to do that, like I'm doing here today. As part of that, we launched a new developer hub with resources, tutorials, articles designed specifically for application developers. So we're not going to teach you assembly. We're not going to teach you the specific instructions for like intrinsics and stuff like that. It's focused on a much higher level at the application developer level, Java, Python, C#, things like that. So some really good resources there. We also have a public Discord for anybody who's interested in joining us there. We've got 6,000 members signed up on our Discord right now. We also have brought a bunch of ARM employees. We signed up folks internal to ARM for what we call our ARM Experts program. So these are engineers, product managers who really know the technical aspect of things, who have said, yeah, we'll come be part of your community and speak directly to software developers and help them out. So you can find a bunch of them in our Discord. They all have that ARM expert role, so you can find them specifically and ask them questions. We also host weekly office hours in our Discord. Every Tuesday at 2 p.m. New York time, I'll be on there. It's an hour of just free chat where you can show off your project, you can ask for support, really whatever anybody wants to talk about. It's kind of an open space that we do, like I said, every week, except this week because I've been here and couldn't do it. Actually, we did do it this week because my coworker, Robert Wolf, was running it this week. We have a community forums also. This is a great place to get technical support. Those same ARM experts are on the community forums answering questions as well. And a lot of that support and answered questions are available there for you to find. Usually, whatever question you have has been answered somewhere already. This is better than Discord for keeping track of that. We also launched last year what we call learning paths. These are step-by-step tutorials for specific use cases. So for installing a specific program or accomplishing a specific task, whether that's on a microcontroller, a laptop or desktop, or on a server. And these, just like our ecosystem dashboard, are all backed by a public GitHub. So anybody can contribute learning paths. We've had software developers from a bunch of different companies now contribute learning paths to this site. I encourage everybody who's got a software project that they're working on to consider doing that as well. It's really easy. It's just Markdown. There's actually a learning path that walks you through the entire process of writing a learning path. I've done 3 so far myself, and it is a nice, easy to follow process. And then we have our developer program where you can join up to get additional access to ARM experts, to resources, to announcements about when we're going to be at events so that you can come by and see us. As part of our developer program, we also have ARM ambassadors. These are people who are either doing a significant amount of work on some kind of ARM hardware or doing education around ARM hardware. We open up the Ambassadors program for applications every few months. And ambassadors, in addition to the regular benefits that developer program members get, they have weekly calls with our ARM experts, monthly calls with our ARM experts. There's also some financial resources available to them if they need access to specific hardware to complete a project, or they want to give a talk at an event and they need us to buy a ticket for that. There is a financial process or financial resources there available to ARM ambassadors for that. They also get invited to events. Oftentimes when we're sponsoring an event, we will have a whole bunch of tickets, and we will offer some of those to our ARM ambassadors. Next month, we're going to be at Microsoft Build, and we've got 3 of our ambassadors who are joining us there for that on our dime, which is a really nice kind of benefit. All right, so coming to the end, some takeaways that I hope everybody got from this talk. First of all, ARM is more than just Raspberry Pis. It is a nice little 4-core board, but it is not what you should be thinking about when you think about running Java web services or microservices on ARM. You should be thinking those high-performance Neoverse cores and the various cloud instances that are running those. And those cores are taking over the data centers. They are cheaper for the data centers to run. They cost Amazon less money to power them. They cost a lot less to cool them because they run a lot cooler than x86. So all of the cloud providers are bought in on this. It's going to save them money. They are passing that money on to you as customers also. So expect that you're going to see more and more ARM instances in the cloud over the coming years. It's only going to start taking over more of that. But the good news is that the tools and platforms that you use for your applications are already ported over to it. They've already done the work to make sure that your applications will run on these new instances. So with the exception of a few edge cases or some really old software that's only available in binary, you should be covered. And there's broad support within the Java community for this. It's not just ARM doing the work. There is no ARM JDK for ARM CPUs. It is OpenJDK, it is Bellsoft and Azul and AWS and IBM. They're all supporting this. They see that that's the future, and they're already getting there. But all of that makes Java application migration really easy. You've already got the write once, run anywhere benefit from using Java. You can build multi-arch containers now so that you can deploy one container image that supports both x86 and ARM. All of your deployment tools will use those and be able to deploy those out onto these instances. So your job as a software developer, migrating to ARM is going to be remarkably easy. And that's why the future there is now. It is the time now to start working on that. If you're not already, everything's there for you. There's nothing holding you back. Join our developer program, come figure out how to do it, and let us help you get there. Thank you. All right. Are there any questions? Yeah.
Yeah, so basically what, developer? How would this actually impact me? If it would.
It depends on, are you doing the DevOps side of things too? Do you have any role in the deployments? Or do you just write the software and then somebody else handles where it's going to run? Okay, then it's probably not going to impact you much at all. But if somebody says, hey, we need to make this run faster, cheaper, tell them, hey, you should be running it on faster, cheaper instances in the clouds. A lot of DevOps people, they don't know that this is an option for the software that they're deploying. So just let them know that they should try it out. Yeah.
So I love ARM, by the way.
Thank you.
I'm programming, I'm doing x86, whatever, switch over to ARM. I actually built my own version of Linux on ARM.
Oh, yeah?
And so, yeah, and it works great. Do you guys have any, I know you had a developer program for developers come in. Do you guys have any program that helps kind of generate ideas. Because I wrote this, it took me forever to build this OS. It is all on ARM, and I was like, it's just sitting there collecting dust. And I just wanted to, I had some, y'all had the ideas on what I can do, because it runs well, and I have Java, I have Python on it and everything. I just haven't thought of what I want to do with it.
I would say come share it with our community. Our Discord specifically, we've got Discord in addition to just being a chat. They've got a built-in forums thing too, which a lot of our users are using to share the projects that they're working on and get interest from other people that way. And join one of our office hours and show it off. Those are always a fun time to show off projects that people are working on. Right, any other questions? I am working on that. I'm used to working at a startup where I could do basically whatever I want in terms of developer outreach. ARM is very strict about all kinds of IP. So I'm still working to figure out whose approval I need to get to post these somewhere for a public download. Yes. So my Twitter's there. The QR code is to my LinkedIn. Anybody who's interested in the slides or the information on the slides, join our Discord. I'm in there all the time, and I can share any of that information with you there. All right, and just to wrap up, I want to say there's one more session happening right after this one. It is everybody's least favorite session to be a speaker at, the last one of the conference. So I do encourage everyone to go find one of those and support the speakers unlucky enough to get that last time slot. All right, thank you, everybody.
Thank you.